Cool. Yep. Thank you for the introduction, and yeah, thank you for inviting me to talk today. It's been a very interesting event so far. So yeah, I guess first of all, I was asked to. We'll see if this works. Oh, come too far now. There we go. That looks like it works now. So yeah, I was asked to ask what does SuperGen mean for me, and yeah, I guess I started my PhD in 2008. That again is starting to get a long time ago, as I think many people have been saying, but it's been a very interesting time over that time. And I think really being part of the SuperGen for me meant I got to meet many academics all over the UK. This has been very good sort of in future to create networks and get back to those people, those academics that were in there that I know, and then try and work with them in future. For example, I think we just going to start a PhD with Dan Vett, who was also in the SuperGen consortium. And the side effect of that as well is that we had regular meetings all around the UK, so I got to see a lot of cities in the UK. Maybe it's not as glamorous as an EU project where you get to travel around Europe, but yeah, I got to see Birmingham and places like that. The other thing was I got to collaborate with key industrial companies such as Johnson Matthey, Intelligent Energy, and Ceres should be on that list too. And Johnson Matthey being on that list, I didn't know them before doing the SuperGen conference, and that really enabled me to talk to the people as they can't attended the conferences, and sort of been my way into the company. It's enabled me to then develop together. We did a few grants together, and then eventually I did an interview and joined the company. And part of that is because SuperGen is also doing some very, very interesting, PhD work, and my work in particular was, quite fundamental on the electrocatalysis of, fuel cell catalyst, and this really put me in good stead, to join Johnson Matthey, who was, has a heavy influence in fuel cells. So yeah, what is our focus really? So if you look at a PEM fuel cell, you sort of have a proton exchange membrane with an anode catalyst and a cathode catalyst on each side, and then this is boxed in between a gas diffusion layer and porous transport plates. So Johnson Matthey being a chemical company, we really like to focus on the chemical components, and therefore we look at the CCM, the catalyst coated membranes, that is just the anode, cathode and membrane. And we really want to try and optimize this as much as possible to make it easier to commercialize. And our main focuses at the moment, obviously the first one being the anode catalyst layer. This is typically iridium. Iridium is sort of what you call the best trade-off between activity and stability. Ruthenium is slightly more active, but is not as stable. So we generally work with iridium, and also iridium is extremely rare material. So we've got to be selective on how we use it. So there's quite a bit of focus on trying to thrift this catalyst, and you can see in the plot on the left. We can do this quite successfully, so we can take a precursor and then make different iridium oxides to gradient, and this can give us a really good activity relationship. But also, generally as a rule, as it becomes more active, the catalyst becomes less stable. So you really have to then tune your catalyst for the activity stability that you're looking for. So how long does an electrolyzer want to last versus how much production do you want, to reduce sort of like the footprint of the electrolyzer. And then another area that's very important is the membrane. So the membrane is one of the biggest factors in the electrical resistance increase, especially at high current densities. And therefore we really need to reduce this. So here's just sort of a quick graph where we've taken sort of like a reference membrane in the red, and Then we've tried to think, okay, if we make a thinner membrane, what happens to that? And that gives the green line, where you get much more hydrogen crossover. And hydrogen going into the oxygen stream is not a good idea. So this really needs to be reduced. So how can you reduce the membrane but still not have hydrogen crossover? And that's really where we start to get to crossover mitigation. And here simply shown by one with the blue line. I believe that's where we sort of half the membrane thickness, but we've still managed to keep the crossover below the benchmark membrane. And this can be done in a variety of ways. One example is recombination catalyst that actually just then react the hydrogen and the oxygen together. These two processes, so sort of like 15 of the iridium oxide and reducing the membrane, it is really looking at reducing the amount of iridium per sort of gigawatt used. And we really like to play around with a unit called a kilogram of iridium per gigawatt of electricity. And if we can get that as low as possible, this makes electrolyzers much more favorable. The final thing is the stability, really. So one of the degradation mechanisms is that as oxygen crosses over through the membrane, it can also recombine on the cathode side to produce hydrogen peroxide. This can then go in and form radicals and attack the membrane, causing membrane thinning. So we look at additives into the membrane to try and reduce this. So you can see here that we have kind of like, we're looking very much at the system level. So we're looking at combining all of the technologies into a CCM to make sort of like a multi-component electrolyzer. And then sort of one of the great things about working for a big company is that there's sort of lots of input, not just from your field, but from all areas of the company. And here I just want to talk a little bit about that. So the first box on the right is, talks about science. So and that's really where I sit. And this is sort of like using our catalyst and membrane expertise to make the best possible components and then optimize for high performance. And that's sort of a picture of a cathode being printed onto a PTFE backing for a decal there. But also to support this, to really drive it into the market, we have our PGM expertise groups. So these, look at the trading and the transportation of PGM, and this allows us to offer PGM cost reductions to our customers. And then also Johnson Matthey's has the largest secondary refiner of PGM, and this allows us to bring iridium oxide or iridium into sort of like a closed loop offering where we can then take used iridium oxide and bring it back onto the market to try and alleviate some of the strains on the supply of iridium.
1 minute to go, Chris.
Oh God, okay. And then we also have a fuel cell business unit that's been going for over 20 years and provides us with commercial expertise and has a big customer basis currently. So this really helps us then take what they know in fuel cells and moves it into the electrolyzer business. And they also offer expertise in CCM manufacturing that we'll bring, and that's really one of our major drivers. We really want to reduce the manufacturing costs of the CCM, and we can pass this then on to our customers who are the electrolyzer companies. I guess I should kind of speed up. So yeah, I think it's a really exciting time at the moment. Here we have sort of the EU Green Hydrogen Initiative say that they're going to be up to 80 gigawatts by 2030, and you can see sort of in 2020 we're near zero. So this is a massive opportunity, and this doesn't include just PEM. It can be any SOEC or alkaline, but the size of the ambition of the target allows all of these technologies to go in. So yeah, if I kind of wrap up, I think it's going to be a very exciting time for hydrogen for all technologies, and we're very happy to be a part of this. And Johnson Matthey has just released a new business unit in this. I think only October last year, so less than a year old. to officially go into this market. And yeah, we have R&D on committed to advanced multi-component CCMs to really give a full product to customers. And lots of experience from fuel cells will enable us to do this rapidly. And yeah, thank you for listening.
Excellent. Well, thanks everyone for speaking, and thanks for joining me now on the panel session. So please, you can unmute yourselves and be ready to speak. So we've collected in a few questions. We'll probably be overrunning ever so slightly because of the tech issues we had before, but we've got a lunch break and we'll restart just probably around 2:15. So I'll kick off with a question for Dan, which is around what are the opportunities for other academics to be involved in the Prosemino model, and is its focus only on hydrogen, or is it much broader than that?
Yeah, I mean, we're completely open to anyone coming and being involved. If you have a good idea, if you are that way inclined, we realise that most academics are not, but there's certainly a subset who are and who need these kind of mechanisms. So yeah, we're very open to academics getting other people getting involved. So what was that, the other part?
Is it just hydrogen? Is it broader electrochemistry?
No, sorry, no. All electrochemical technology, primarily power systems. There are some things slightly stepping outside of power systems, but no, it'd be batteries, supercaps, fuel cells, hydrogen, electrolyzers. Yeah, quite a range.
Okay, great, thanks. The next question is for Shubi. This is an interesting one because those who are familiar with the old days of series power may have a wry smile, but the question is 20 kilowatts a bottom limit for this technology? Any prospects of 3 to 5 kilowatts for domestic customers, which is a huge market?
Yeah, very good question. So absolutely, I think as you see in our licensing model, we have the capability to do 1 kilowatt class all the way up to megawatts. And what is driving the product is really our customers who are coming in and saying, okay, this is what we want for the market. So I think we have a module of a 5 kilowatt and a 1 kilowatt, and we use that as transferring our technology or licensing our technology. And the 30 kilowatts are ganged up 5 kilowatts 6 times. And so similarly, you're going to put together lots of different modules to make up the larger kilowatt. So if 5 kilowatt, there's a market for it and there's a customer for it, we're absolutely for licensing it. That is absolutely not a problem.
There's another question for you, which is around the electrical efficiency for the SOEC for green hydrogen production. And I presume you can give us an answer with or without heat input.
Yeah, so that's again a very good question. So one of the advantages of SOEC is you can use waste heat, and when you couple it to things like steel, and if you do all of those things, the efficiencies are in the 90%. If you don't use the heat, then the efficiencies are in the 70%, so in 70+%. So both of them are very commercially attractive, but obviously, because it is so difficult to decarbonize some of these foundation industries, we see a huge market and a potential for high efficiency for those kind of applications.
Thank you. There's a few questions about temperatures and the relative merits of operating at different temperatures, either for fuel cells or electrolyzers. And I don't know if anyone from the panel wants to pick up on that, whether that's driven by the application or by the efficiency, or maybe someone else from the panel would like to pick that up. Maybe Chris. Any particular thoughts on operating temperature?
Is it operating temperature for PEM?
This is the electrolyzers generally and fuel cells generally. What are the relative merits of different operating temperatures?
Okay. I mean, yeah. I mean, going to higher temperature, allows the kinetics or the resistive losses to be lower. So definitely, you get a higher performance. But the issue is that then you also increase your degradation mechanisms, so you can shorten the lifetime of the system. But I think there is a definite drive to go to higher temperature. I mean, in PEM, quite a lot of, historically it's operated around 50 degrees, and it's pushing towards 80 degrees. But maybe some other people have some thoughts on it too.
I would simply say it's a horses for courses thing here. The more options we have, the better. It depends on the customer. If it's going to be on-site hydrogen, the scale. Do you have dynamics? Are you going to be taking something from a wind farm, or are you going to be taking power from a nuclear power station? Is there free heat available? And I think you've got this kind of spectrum of different technologies, which are largely kind of dictated by their temperature of operation. And I think there's a place for all of them.
Yeah, so it's a systems issue in many ways.
Yeah, if I can add one to that, as people that are putting thermal management systems into vehicles, we're often ending up with 3 thermal management systems, because you've got devices that operate. So you've got batteries down at 30 odd degrees, you've got a fuel cell at 60, 70 degrees, and you've got power electronics that would be higher. If we could get the fuel cell to operate comfortably at the same temperature as power electronics, that'd be magic. So from a size of radiator, you look at the Mirai with an enormous grill on the front. So size of radiator, the physical packaging, and just the simplicity. I'd say there's a driver on the integration sense for higher temperature, and they tolerate lower efficiency because it's a capability to put it together kind of consideration.
Another question for you, Ben. Are you thinking of hydrogen-powered marine applications?
Yeah, so we've looked at them at various points. I think we just won a contract to do I think it might be it's in a port rather than actually on a boat. But yes, the only reason we haven't done it really is we follow where the market goes. So marine is starting to pick up quite a bit. So yeah, simple answer is yes. Marinization of fuel cells and power electronics and things is, enough work's been done on that to, I think, not have it as an issue. Obviously, it needs to be considered. Where we've been asked, and we've modeled at various points over the years, marine propulsion. One of the challenges with marine propulsion is it's incredibly energy hungry. If you're going at a couple of knots, pretty efficient, quite practical to do, not using a liquid fuel. Once you get up to high speed, it starts to get quite tricky. We've got a couple of conversations running with people, some on their NDA, but let's say generally looking at less conventional, not displacement ship vessels. So if you've got a load of stuff under the water, you got to push it through the water, it takes loads of energy. Get it up above the water, it takes less energy. So as always, really, I suppose the efficiency of the vehicle makes it much more practical to move away from diesel.
Right. And apparently you had a hydrogen hackathon in 2015, which was a good outreach activity. Are you planning to do another one?
Yes. So in fact, there's a big program for COP26. So I get into trouble if I sneak and announce it. There's a program coming. The sponsors may be on this call, so I won't say too much. But yeah, there's a nice program coming around COP26. And yeah, various other things happening. And if anyone would like to sponsor any, we can do even more. But yes, yeah, plenty more of that. And they work really nicely. So it's good stuff. So yeah. And we had great collaboration with a lot of the universities, I think, on this call as well. So your involvement in that is critical.
Excellent. We've got a question for Dan. It's from Tim Mays, but I think every academic that is participating in this webinar will also be interested. So Tim says to you, Dan, as an academic, almost all of my time is taken up doing research, teaching and admin on campus. Where on earth do you get the time for all your spin out, etc. activities?
Well, that's a very, very good question. Actually, I get up very early, so I do the kind of spin out stuff between 5:30 and 9 in the morning, and kind of do as much as I can for the normal day job, and then if I'm still kind of in the land of the living, into the evenings and weekends. But it's a different kind of motivation, and it's a different kind of it's a lot of it's hard work, in which case the hours are hard, but a lot of it is really good fun. So for those academics who are interested in doing these things, give it a go. You learn so much, and actually I think it enriches your academic part of your life. Great.
So it's almost I suppose something that gives you so much motivation you don't necessarily see it as work.
Get it all done before 9 in the morning, and
that sounds like a plan. Well, that's a very good note to end our session on. So thank you all very much. I really enjoyed your talks, and I can see really a lot of renewed optimism for the sector, and really a lot of excitement. So I hope our listeners and viewers also got the same feeling.